Look at the Chinese A-share market. High retail participation, strict T+1 settlement rules, and daily price limits create an environment where asset prices constantly deviate from their rational value, driven by pure emotion. Decades ago, traders in red vests shouted across crowded floors to capture these short-term pricing anomalies. Today, millions of lines of code execute those same trades in milliseconds. The physical tools look completely different, but both generations of traders are trying to solve the exact same problem. Modern quantitative trading is dense with complex terminology, multi-factor regressions, deep neural networks predicting price trends, dynamic asset weighting. If you strip away the computer science terminology, every single one of those strategies collapses into one pure mathematical concept. That concept is unconstrained nonlinear programming. This is a class of mathematical problems where the objective is to find the best possible outcome in a space that has no strict boundaries, but where the rules governing the space curve and change unpredictably. The absolute goal of this programming is to find the precise combination of variables that minimizes a specific objective function. That function might represent the expected maximum drawdown of a 500 stock portfolio, or it might be the error rate of a machine learning prediction model. Forcing that function's value as close to zero as possible, finding the absolute lowest point, is the unglamorous mechanical source of quantitative alpha. Optimization algorithms share an inherent physical limitation. They cannot look down at an entire dataset, from a bird's-eye view to simply point out the lowest spot. Instead, the algorithm operates exactly like a blindfolded climber dropped into the middle of a vast, jagged mountain range, using only a stick to tap the ground. The invisible, overarching topography of this mountain range represents the objective function itself. The absolute lowest valley floor, hidden somewhere in the dark, is the ultimate answer the algorithm is trying to find. The climber's exact coordinates on that mountain represent the high-dimensional variable vector. In a real trading scenario, that single position might dictate the precise dollar weight assigned to hundreds of different stocks at the exact same time. Because the problem is unconstrained, there are no walls or fences stopping the climber from moving in any direction. Because it is nonlinear, the slopes are deceitful, filled with steep cliffs, twisting ravines, and flat false bottoms. Without global vision, the algorithm has to navigate this treacherous terrain using only the mathematical geometry of the ground immediately beneath its feet. So how does a blind algorithm decide which direction to take its very first step? This 3D diagram illustrates the algorithm's first-order mathematical compass, the gradient. It calculates the local slope and points toward the steepest incline. To minimize the function, the algorithm calculates the gradient and moves in the exact opposite direction, the negative gradient, to descend. This process is governed by the line search framework, requiring the algorithm to execute a strict two-part rule. First, choose a direction. Second, choose a step length. The negative gradient easily provides the fastest immediate direction down the mountain. Relying entirely on the steepness of the present slope without looking ahead leads to catastrophic errors. To test these algorithms, mathematicians use the Rosenbrock function. It is a mathematical formula known as the banana function due to its pathological U-shaped topography designed specifically to trap optimization algorithms. This exact topological shape occurs frequently in real-world finance. If a portfolio contains highly correlated assets, like two competing tech stocks in the same sector, their combined risk profile creates a long, flat valley, flanked by incredibly steep, curved walls. When the standard gradient descent algorithm falls into this valley, it behaves greedily. It blindly seeks the steepest immediate drop, completely ignoring the macro curve of the landscape. This contour map displays the failure. The blue path violently bounces back and forth across the steep walls, making almost zero forward progress down the valley. As the step counter ticks past 5,000 iterations, the algorithm burns massive computing power while remaining permanently trapped. Gradient descent fails because it lacks foresight. It calculates the present steepness perfectly, but possesses no mathematical mechanism to anticipate future curvature. To fix this, the algorithm needs a second-order derivative. Instead of just calculating the slope, it needs to calculate the rate of change of that slope, the curvature. The solution lies in an optimization technique developed centuries ago, Newton's method. Newton's method introduces the Hessian matrix, a square grid of second-order partial derivatives that strictly represents this multidimensional curvature in a format the computer can process. Look at this 3D surface model. Using Taylor's theorem, the algorithm combines the gradient and the Hessian matrix to build a local, predictive wireframe parabola that perfectly molds to the terrain's exact curvature. On the same Rosenbrock terrain, armed with curvature data, Newton's method plots a red dotted line that slices smoothly down the center of the valley, bypassing the walls entirely. The algorithm reaches the absolute minimum in exactly 31 steps. Newton's method succeeds in complex financial modeling because it uses second-order derivatives to mathematically anticipate the behavior of correlated assets, rather than blindly bouncing between them. Once the algorithm knows the correct direction, it must make the second choice in the line search equation, determining the step length, represented by the Greek letter alpha. If the chosen step length is too large, the algorithm will completely overshoot the valley, throwing the coordinates into an unpredictable area and destabilizing the model. This line graph demonstrates the Armillo condition. The Armillo condition is a strict mathematical boundary requiring the objective function to drop by a specific proportional fraction of the initial gradient. The diagonal tangent line establishes the threshold. Any step landing above it is rejected. Here lies the practical engineering problem. Calculating the absolute perfect step length at every single iteration requires solving a complex one-dimensional optimization problem, which takes too much computing power and time. In actual quant coding, theoretical perfection is replaced by a pragmatic, brute force alternative known as the backtracking algorithm. Backtracking operates on simple logic. The algorithm guesses a large step size. It checks if that step violates the Armillo condition. If it does, it shrinks the step by a fraction repeatedly until it mathematically fits, ensuring it drops far enough to make progress without overshooting the valley. It abandons mathematical perfection to guarantee real-world execution speed. With the direction and step length secured, these individual mathematical components are assembled into the final optimization loop. This flowchart outlines the heartbeat of the quantitative machine. Calculate the derivatives, confirm the Hessian matrix is positive definite, pick the direction, backtrack the step size, update the coordinates, repeat. This loop cycles continuously until it hits a hard termination condition. It stops only when the change in risk or prediction error falls below a microscopic predefined tolerance. In the reality of the A-share market, finding the absolute global minimum across thousands of stocks with millions of data points is a computational fantasy. The landscape is too vast. But the algorithms are not designed to find perfection. A sufficiently optimized local minimum provides a high enough Sharpe ratio and a low enough annualized drawdown to deploy real capital. No global view of the market exists. Alpha is captured by reading the local geometry of the data and taking one perfectly calculated mathematical step in the dark, over and over again.